Well, greetings for Taco Tuesday. John Barba along with Dave Holdorf from Taco Comfort Solutions, and welcome and thank you folks for joining us. We really appreciate the gift of your time on this Tuesday. I hope it's warm where you are. It's not terribly warm where we are here in New Hampshire and on Long Island. Winter is starting to approach. It's still technically fall, but the days are getting shorter and the evenings are getting darker and a little bit cooler. So it's heating season officially, right, Dave?
That's right. That's right. As far as I'm concerned, heat's still running this morning. I came in and floors were nice and warm, so I was all happy.
Oh, all right. Very good. Very good. Today's topic is wiring for hydronics, understanding what's in the boxes. And this is the first of a two-parter. Again, we're going to do a kind of an overview on basic electronics for hydronics today and talk about some of the fundamentals of circuitry and things like that. And then in 2 weeks, we'll do a deep dive into TACO's residential hydronics controls, our SR, circulator switching relays, and our ZVC zone valve controllers. Plenty to dive into there, and that'll be in 2 weeks. Today, we're going to talk about just some fundamentals of electronics so you understand what these things are trying to do and understand some of the terminology. All right. As always, please view this as treat this session as you would treat a classroom exercise. If we were in a classroom together, what would you do? You wouldn't be checking Facebook, I hope, all right, or Twitter or whatever, checking emails. Um, our goal is to try to keep you engaged, all right? Your job is to try to stay engaged. So if you can resist the temptation to do a little surfing while we're talking, that'll help you guys out. Also treat this as a classroom experience by grabbing a pen and a pad of paper, all right? And take notes, write stuff down. It's not going to distract you from paying attention. It's going to help you pay closer attention. It's going to help you get a little bit more out of this, and you'll have a written record. So take some notes. This is being recorded. About this time tomorrow, you're going to get a follow-up email with a certificate of attendance, as well as a link to the recording, so you can go ahead and view the recording as many times as you wish. But do take notes. That'll help you out. And the other thing is that's going to be real important is to ask questions. Whenever they occur to you, type them on in. Now, where do you type in the questions? Well, on your control panel, you should see a little area there down at the bottom that says chat/questions. That's where you're going to type in your question. So if you could do something for me right now, just say hi, hello, how are you? Just so I know that you know how to do it and that I know that we are actually broadcasting and you can hear us and we haven't lost our internet connections, which happens from time to time. Both Dave and I have had the misfortune of losing our internet connections midstream, and we just keep yakking away and we don't know.
That happened last night too. Yes, it did.
Yeah,
So thank you for everybody that is jumping in there and typing in some comments for us. Greatly appreciate those things. I do want to point out one error on the screen that you're looking at the moment. You do see the title of the class, and at the bottom it says presented by myself, Dave Holdorf, but unfortunately I cannot stay. So JB is going to be taking over for me today. I will not be able to do the presentation. So John is going to do the class. I have to leave in a few minutes. But one of the things I love about this class here, because I know some people have come to this class that I've done out in the field back when we used to do live stuff and say, well, I really wanted to learn how to use the controls or troubleshoot the controls. When we go through this stuff today, what you're going to see is, the stuff that's inside the box, what's on the relay board. And I hope that can help you understand what happens on the inside, and what the individual components are rather than just a wire here and a wire there. And that we'll go over the next time. Wiring point to point is what we're going to go over the next time. But I think sometimes we throw terminology around and we hear it so often that we really don't pay attention to the meaning of the word anymore. So we're going to do that today. So John is going to do that today too. So that is, unfortunately or fortunately, depending on how you look at it, I will not be around.
It's interesting you bring that up, Dave, because when I was in the trades, when I was working with my dad's company, we put in relays all the time. We didn't wire anything. We were the pipe fitters, and what was in that box was magic, right? We didn't really know it, and I didn't really understand how a relay worked until I was put in the position where I had to teach someone how a relay worked. So I figured if I'm going to have to teach someone how a relay works, I better learn how a relay works. So that's kind of how we see a lot of folks in the field. Is this box just it goes click click click, and the thermostat tells the pump to start and the boiler to fire.
Right.
Great.
And it's got
That's
lights.
cool. And it's got lights. How does it do that? What's the process? And what do these little doodads and doohickeys inside the box actually do? That's what we're going to talk about today. So we're excited for this. And again, questions, when you have them, throw them out in there. So we're going to start with a little primer on low voltage wiring, just so we understand how it works, what it is. A lot of the wiring we're going to show you is low voltage. A lot of the same principles apply to line voltage, especially when we convert line voltage to low voltage. It's all kind of the same idea. We're dealing with circuits and switches and things like that. First, just some stuff we need to know, basic understanding and knowledge of what we need to know. All right, we're going to start real simple. Thermostat. Okay, what is a thermostat? For a lot of people, the thermostat is the single most important element of their entire heating system. It's the only interface most people have. Um, One of the things that comes up quite often is, when you ask people what kind of a heating system do you have, do you folks, type this in. When a survey there's been a survey out, there's surveys done out there about heating systems. When people ask, what kind of a home comfort system do you have? Do you folks know what the number one answer is? And this number one answer has been number one for a long time. Type it in if you know it. Mike Boyd, I see you have it. Yeah, absolutely. Mike's got it. Anybody else? Type it on in, see if you know. Yep, Eugene's got it. David, close. That's David number two. That's the second most common answer. Jerry's got it. Yeah, when people are asked what kind of a heating system you have, they said their number one answer is Honeywell. I got a Honeywell system. How do you know? It says on that round thing on the wall, Honeywell. Okay. The second most common answer is actually isn't the second most common answer isn't furnace. It's gas. The second most. So your customers out there don't really know. Maybe they've got a little bit more understanding as technology has become more commonplace. They might have a little bit more understanding, but still understand this little switch on the wall is the only interface most folks have with it. It's the extent of their understanding of their systems. And a thermostat, anything with the word stat in it, let's put it this way, anything with the word stat in it is a switch. All right, a thermostat is an air temperature switch. It's prompted by the air temperature that it senses in its general vicinity. So a thermostat is an air temperature switch. Then you have an aquastat. Again, the word stat indicates that it is a switch. An aquastat is a water temperature switch, hence the word aqua. Okay, so it's a water temperature switch, whether it's a strap-on type, an immersion well type. It's a water temperature and it does whatever it does. Okay, once it senses a water temperature, it closes, the switch closes or opens. And we'll get into that in a second as well. And then you have a relay. A relay is an electrically operated switch, an electrically operated switch. This is an old style ice cube relay. Most of them have been replaced by solid state relays, but in older systems, you're likely to see something like this. And this little relay takes you back to Cub Scouts. If you were a Cub Scout, you had to do something like this to get your wolf badge, all right? And what you have is a hunk of metal with copper wire wrapped around it. And when you run current, electrical current, through that copper wire that is wrapped around a hunk of metal, what have you created? Well, you've created an electromagnet, right? When you create that electromagnet, that's what prompts the switch to change positions, okay? So right up here, we see a little switch, and we're going to get a closer look at that in a couple seconds. But that electricity going through the copper wire wrapped around a hunk of metal creates an electromagnet, and that's what causes the switch to change positions. Still more. Dry contacts. You'll hear this term a lot. Dry contacts. A dry contact, unlike our friend here, what our friend is experiencing, dry contact, it's a relay contact where there's no voltage present. All right, there's no voltage present. You have to physically bring voltage to that set of contacts for it to do anything. So there's no electricity at that source. Okay, no electricity at that source. That would be called a dry contact. And then we have isolated end switch. An isolated end switch is generally speaking a dry contact, but it's contacts that make when a zone calls for heat, and it usually denoted in a relay by XX. All right, and that's connected to TT on the boiler. The isolated end switch, when everything else is doing what it's supposed to do, that end switch closes, and it closes a circuit to something else, generally speaking, the boiler control. So that's an isolated end switch. Alrighty, now an interesting concept that a way to think about electricity, and I don't know if this is useful or not, but it's kind of fun to talk about. It's an interesting
Yeah,
concept
I
when
like
it,
to think about it too, because a lot of our installers look at these as they know how to troubleshoot a hydronic system. They know what's going on there. And I thought, this would actually be a good way to, if you don't do wiring, hey, maybe you can, and don't be afraid of it too, because you already know one side. So go ahead. Sorry.
no, glad to jump on in, man. And it's an interesting concept. We are all familiar with the concept of the universal hydronics formula, and if not, you should be. The universal hydronics formula rules hydronics on the wet side, on the water side. And the universal hydronics formula states that GPM is equal to BTUH divided by the product of delta T times 500. GPM, that's the gallons per minute flow rate you need to deliver the BTUs, right? The BTUH, of course, is the BTUs you need. That's what you're gunning for, all right? And then delta T times 500. Delta T is your temperature difference of the fluid as it goes through the system. And 500 denotes the type of fluid. 500 is we use 500 when we're using 100% water. And we get that from multiplying the weight of a gallon of water, 8.33 pounds, times the number of minutes in an hour, times the specific gravity of the fluid, times the specific heat of the fluid. That comes out to 499.8 for 100% water. We call it 500. So GPM is flow. BTUH is the heat that we need to deliver. All right, so we're trying to find out the flow to deliver the BTUs that we need. And the denominator here is delta T times 500, shorthand for the temperature difference. All right, so that's the universal hydronics formula. The same thing, only different, could be something we might call the universal hydroelectronic formula. Okay, kind of it's the same thing, only different. And it's just a way to think about it. So instead of GPM equals BTUH divided by delta T times 500, you're going to look at it like this. Amps equals watts divided by volts. Amps equals watts divided by volts, where amps equals the measurement of electrical flow. All right, it's the measurement of electrical flow. Watts is the amount of energy used. It's also known as VA. All right, you have 40 VA transformers, the same thing as a 40-watt transformer. It's the amount of energy used. And then volts, the difference in electrical pressure. You got 24 volts. You know how difference in electrical pressure. If you put your fingers across a 24-volt circuit, it might hurt just a little. Do the same thing on 120 volts, it's going to hurt a lot. Okay, so it's the difference in electrical pressure. All right. Okay, good way of looking at it, right?
Yeah, I like it. Yep.
Yep, there you go. So difference in electrical pressure. So what does that mean? How does that work? Well, let's just do it in pictures, okay? So here's an old boiler, really old boiler, okay? And let's look at GPM is equal to BTUH divided by delta T times 500. Now GPM is the flow through the piping circuits, the flow of heat through the piping circuit, all right? In gallons per minute. BTUH, of course, is the amount of energy used in the piping circuit, runs through radiators and stuff. All right, that's the BTUs. That's what's being taken out of the fluid and putting into the air. It's what's being used. And then delta T times 500, the difference in temperature of the water, of what's going out versus what's coming back. Okay, it's the difference in temperature, difference in water temperature. So there's your hydronic circuit. Electrically, same thing, only different, right? Amps equals watts divided by volts. So amps is the flow of electricity through a circuit, all right? Watts is the amount of energy that's used in that circuit. And then volts is the difference in that electrical pressure back at the electrical source. Just a way to think about it if you're unfamiliar with the electrical component of what we do in hydronics, just a way to think about it so you can understand it. Why do we need to understand it? Well, we have to be putting things together and we have to understand limitations and capabilities. And that gets us to circuits. Dave, if you're still out there, are there any questions we need to address?
No, at the moment we're doing pretty good. We had a bunch of comments come in between the Honeywell and the gas poll before, but no questions at the moment. Keep on rocking
Okay.
and rolling.
Terrific.
And with that being said, I will be jumping out of here in the next minute or two. So good to see you all, and I will see you all in 2 weeks. Thanks so much.
All right, now that Dave's gone, you're stuck with me. The party's over, folks. We're going to get serious. Good luck, Dave. Hope it works out all right.
Thank you.
Okie dokie. So let's talk about circuits and why we love them. We love circuitry. Circuits are great. So let's talk about electrical circuits. And I don't know if you have this picture over on the right-hand side. When you were kids, did you ever get those little kits that you could like start playing with this stuff and putting things together? And here you got switches where you can make things light up. It's to teach you about electronics and about circuits. And the thing about electronics is everything is a circuit. Virtually everything is a circuit. All right, and in hydronics, the circuits are important. Always think in terms of threes when you think of an electrical circuit. You've got a power supply. All right, a power supply is what creates the power or what delivers the power or where the power comes from. In most cases, it could be a transformer, it could be the outlet in the wall, okay, it could be what the electrician leaves for you. It's the source of the power supply. Also in that circuit, we have to have a switch of some kind. The switch is basically a stop-go kind of thing. It tells the electricity to go or to stop. One difference in terms of switches, a switch in electronics is kind of like a valve in hydronics, only backwards. All right. In hydronics, if a valve is open, that means water can flow, right? And if it's closed, that means we stop. It's the exact opposite in electronics. If a switch is open, think about a drawbridge, all right? If the drawbridge is open, the electricity cannot flow. It can only flow when the switch is closed, all right? So it's the exact opposite of a valve. So when the switch is open, no electricity flows. When the switch is closed, the electricity can flow. And that's important to the final part of the circuit, the load. It's the thing that uses power to do work. Uses power to do some sort of work. So again, here's your open switch, no flow of energy. Closed switch, the load gets the power to do whatever it is supposed to do. So open and closed, open and closed. All right, very good, very good. Now let's talk about power supplies. Again, where the power comes from. Again, it could be the outlet on the wall. It could be, as far as we're concerned, it's the panel in the building. It's whatever the electrician leaves for us. That's the power supply. It's where it comes from. And they can be line voltage, or in the case of a transformer, low voltage. Now, yeah, there are step-up transformers. In our world, we typically deal with step-down transformers that turn line voltage into low voltage. And a lot of people say, well, it does it by magic. That's silly. Of course it doesn't do it by magic. Anybody know how a transformer, type this in if you know it, how does a transformer turn line voltage into low voltage? Type it in. Let me see what you got. How does a transformer magically turn that line voltage into low voltage? What happens? How does it do that? And I'll wait for you to type something on in. Waiting, waiting. Let's see what you got. We got we've got magnetic induction. We have Nicholas saying a flux capacitor. I like that. Jason says magic. All right, magic. We got coils, two coils, magnetic fields through the loss and windings, etc., etc. Yeah, well, sort of, kinda. Yeah, sort of, kinda. The real answer to me is smoke. All right. How does a transformer turn line voltage into low voltage? The answer is smoke. Inside this black enclosure right here, you got line voltage on this side coming in. Over here on the secondary side, you've got 24 volts coming out. Inside this black enclosure is factory provided smoke. Okay, it's factory provided smoke that turns that line voltage into low voltage. Because, yeah, you guys have come up with that. Yeah, James and Alan. Have you ever overloaded a transformer? If you have, what comes out of that transformer? It's smoke, right? Does the transformer work anymore? No. As far as we're concerned, it's smoke, right? Smoke turns line voltage into low voltage. If it fails the smoke test, we're out of business, okay? So just think of it in terms of that. You want to keep the smoke inside the transformer at all costs, at all costs. So again, there are step up and step down transformers. And again, as we said, they turn line voltage into low voltage. And transformers are rated in terms of VA, volt amps, also known, of course, as watts. And that rating is kind of sort of like BTUs in a boiler. If you think of the transformer as a boiler, you can think about it in terms of capacity. What can it do? What are its capabilities? All right, so let's take a look at what that is. It's just sort of like a boiler, only different. let's say I've got a gas boiler that has an absolute net rated output of 40,000 BTUs. All right, that's the net output of the boiler. So it delivers 40,000 BTUs. That's it, 40,000 BTUs. Can it do more? No, not really. It can't. It's 40,000 BTUs and that's it. You put a 40,000 BTU boiler in a house that needs 100,000 BTUs. When push comes to shove, that boiler can't heat that house. All right, so we understand the limitations of boiler capacity. Well, transformers are kind of the same thing, only different. A 40 VA transformer can deliver 40 VA or 40 watts. Can it do more? Sort of, kinda. Can you overload a transformer? Transformers have something built in called impedance protection, meaning if you do happen to overload it for brief periods of time, what happens is you can overload it, meaning you can put more than 40 VA worth of load on that for a very short period of time. What'll happen is the volts will go down. Okay, the volts will go down. So instead of it being delivering 24 volts, it might drop to 22 or 20 or 18. In terms of a zone valve, what that might mean is the zone valve action will slow down. Okay, it will slow down. And that's built-in protection. So intermediate or intermittent overloads won't blow that thing. Think of impedance, think of a transformer, think of it like in your car. If you're driving your car and you're watching the tachometer, can the tachometer go into the red? Well, sure it can. Intermittently for a little bit, yeah. But if you tried to drive 200 miles with the tachometer pinned in the red, you're going to blow the engine. It's the exact same thing with a transformer. If you overload it for an extended period of time, you're going to let the smoke out and we'll have to get a new one. All right. So that's how to think about a transformer as you would think about a boiler. Now, yeah, all of you had the windings. Absolutely, it's windings. It's pretty simple magnetic induction. It's windings. So on the primary side, which is the line voltage side, you've got 500 turns, 500 a hunk of metal with copper wire wrapped around it, right? And you've got 500 turns on the primary side. Over on the secondary side, the low voltage side, you only have 100 turns. So that gives us a 5-to-1 ratio, a 5-to-1 ratio. And if we think about 120 volts to 24 volts, that too is a 5-to-1 ratio. It's a 5-to-1 ratio. So that's how we turn the line voltage into low voltage. Of course, inside here is that smoke that will help with the conversion process. All right, good, excellent. Now let's talk a little bit about loads. Loads, as we said, they use power to do work and they come in all different forms. Any kind of a motor or a coil, okay? So the motor in a circulator, that's a line voltage load, all right? It's a line voltage load. The motors on zone valves, whether it's the old 571 from Taco or the Zone Sentry, the motor uses 24 volts to do work. Down at the bottom, you see a little manifold actuator for a radiant manifold. It uses power to open, all right, to push itself open. And up on the right-hand side, you see a coil from a relay. The load in that coil is the coil. The load in that relay is the coil itself. We're wrapping that copper wire on a hunk of metal to create an electromagnet. That is the load in a relay coil. All right, and then we also have a switch. We also have the switches there, but the loads use power to do work. And then finally, we have switches. Pretty simple. Turn something on or off. Tells the power to stop or go. All right, pretty simple stuff. And there are a whole bunch of different kinds of switches. You've got thermostats and aquastats. As we said, anything with the word stat in it is going to be a switch. What else? Well, we've got low water cutoffs. And in our zone controls, our zone valves, you'll also have an internal end switch in many of them. Some of them don't, but most of them do. Our zone valves have an internal end switch, which once the load has done what it's supposed to do, which in the case of a zone valve is force the zone valve open, internally an end switch will close, and that'll be the switch for a completely separate circuit. All right, and then something else is going to happen downstream. So you'll see again, end switch on the back of a Zone Sentry zone valve. You'll see two sets of terminals. One's for the end switch and one's for power. All right. Types of switches: normally open or normally closed. All right. Normally open is pretty straightforward. When nothing's going on, the switch is open. Something has to cause it to close. Something has to change. All right. A lot of times people say the acid test. If you're holding it in your hand, what position is that switch in? Is it open? Well, then it's a normally open switch. A thermostat would be considered a normally open switch. When you're holding it in your hand, normal situations, that switch is open. Something has to happen for that switch to close. That means the air temperature has dropped to below whatever the set point is. So that's a normally open switch. Then you have a normally closed switch. And again, same thing, only different. You're holding it in your hand, that switch is closed. Something has to happen in order for that switch to open. A safety switch, a low water cutoff is a perfect example of a normally closed switch. That switch is closed, so it's allowing current to go unless the water level drops below the probe. Now we don't have enough water in the system. That's going to cause the switch to open and it stops everything. All right, so a safety switch is typically a normally closed switch. Types of switches: single pole, single throw. Single pole, single throw. Single pole, single throw is about as basic of a switch as you have. It's one pole and one contact. All right, could be normally open, could be normally closed, doesn't matter. But it's just one thing. Something has to happen for that switch to either open or close. It's an inline switch. One does one thing for one circuit. All right, normally open or normally closed. So something has to happen. Again, a thermostat is a single pole, single throw switch. All right, a light switch, single pole, single throw, same thing, only different, sure. And thermostats and aquastats, as we said. Now, let's have a little bit of fun. You can have a double pole, single throw. It's the same thing, only twice as nice. So one thing can cause two circuits to close. So one instance can cause two circuits to close, and then two different things will happen. All right, two separate circuits. It's in one relay cube or one relay. One thing happens, both circuits close, both switches close, two circuits will go ahead and do something. All right, in downstream. So one action will close two separate circuits, so two things can happen. So that's a double pole, single throw. Then you have single pole, double throw. And that's your basic either or switch. It's an either or switch. All right. First, when you're holding it in your hand, you've got two contacts here. So it's one thing can be an either or switch. The normally closed circuit is closed. All right. Then something happens and what was closed will now be open and what was open will now be closed. All right. Where might you see a single pole double throw switch? Anything to do with domestic hot water priority is an either or switch, right? Domestic hot water priority is either or. So when you have domestic hot water priority, you've got a single pole double throw switch somewhere in the setup. All right. We're making heat. Okay. We're making heat. That's the normally closed circuit. Your priority zone, the domestic hot water tank, the indirect calls for domestic hot water. We want to go into priority. We shut off all the heating, the heating portion of the system, and now everything that boiler has is dedicated to making domestic hot water. We go here. So what was open, the domestic hot water circuit, is now closed. What was closed, the heating circuits, are now open. So we stop that, we do this, okay? So there's your single pole double throw switch. And then you get into a relay. You're kind of your basic relay that you'll find in a single pump relay. It's a double pole, double throw. It's two either or switches. All right, it's two either or switches. So it's kind of the same thing. And here you see a picture of again, everything's now is solid state, but this is a good example of what that would look like. Okay, you have, if you can see my cursor right here, you have a single pole, that thing in the middle, all right, and then your two different contacts. So it's a single pole and it's either here or here. So it's single pole, double throw. Right now, because we're holding it in our hands and it's not connected to anything, this, of course, down at the bottom, that's the normally closed circuit. And then if something were to happen and we were to energize this coil and make this thing go click, what we're going to do is basically send that switch into the other direction. All right, so it's a single pole double throw. And in relays such as this, you'll have two sets of switches. So it's one action makes both switches go click like that. Double throw, double pole, double throw. Very good, very good. Now we can have switches in series as we show here. Here's a line voltage circuit for a burner, for an oil burner, all right? So we've got line voltage, and then we have these two normally closed switches, the service switches, that switch up at the top of the stairs. We want to keep that closed so we get power. It's an emergency switch, so you shut that off if something goes wrong or you need to service everything. So there's that switch up at the top of the stairs. And then let's say we have a low water cutoff, a safety low water cutoff. Again, normally closed because if we had a leak or something and the water level went down, we want that switch to open and break the circuit. All right, so the service switch could be closed, but we want to make sure we get nothing else going on if there's a call for heat. And then there's the high limit, which is in the boiler control, which is going to be open until we hit or going to be closed until we hit our high limit, and then it opens. All right, and then it closes when we go down below our differential. So here you will have a bunch of switches in series that we need to make sure that we need to ensure safety and proper operation. All right. Now some more stuff. Let's look inside of a relay, if you will. Again, this is a two-zone relay, one of Taco's two-zone switching relays for circulators. So a switching relay, that's the SR in our SR series, switching relay. You have a transformer and a set of relays in one box. So we bring in line voltage, all right, and we convert it to low voltage for half of the circuitry, and we still use line voltage for the other half in order to power our circulators. So up here, you'll see the isolated end switch right here, the isolated end switch. And here's a pop quiz for you. What kind of a contact is that? What is it in terms of poles and throws? And is it a dry contact or is it a powered contact? What do you guys think? Let's see what you got in here. So the isolated end switch, XX, all right. James got it. It's a dry contact. There's no power there. We need power. It's just a switch, right? It's just a switch, and we need power in something else. And it's open or closed, right? It's open or closed, so it's a single pole, single throw. Single pole, single throw. Now we have our thermostat terminals. All right, our thermostat terminals. To that we connect our thermostats, and again, that's a single pole, single throw switch. It's an air switch. So this connects to these connect to the thermostats. When the thermostat's open, nothing happens. When the thermostat closes, all right, then we start other things happening. What's going to happen is let's view these solid state contacts as those ice cube relays, right? So when the thermostat closes, we complete a circuit between the low voltage side of the transformer and, again, imagine this is the old ice cube relay. Right here we have that hunk of metal with the copper wire wrapped around it. So when the thermostat closes and we complete the circuit, we complete a circuit that will allow that low voltage, that 24 volts, to go around that hunk of metal with the copper wire and to create that electromagnet. And that will then pull the powered relay down here closed that will turn the circulator on. All right. So we've got a switch down below here. All right. We've got a switch for the circulator circuit. We have line voltage brought in as well, courtesy of the ZR and ZC right here. We now have line voltage to these circuits. And then, so we have the switch, we have the power supply, and the circulator itself is the load. So thermostat calls for heat, that completes one circuit. The load in that circuit is the relay coil, and that's what prompts the switch in the second line voltage circuit to close and turn the circulator on. Now up here, our priority switch, what kind of a switch is that? Is it normally open, normally closed, or is it a either or switch? What kind of a switch do we have up there for our priority? That's an enable switch at that point. And once we enable that switch, now we've created the either or, right? It's the single pole double throw, either or switch, either or switch. Excellent work out there, guys. You got it. Very good, very good, very good. I'm hoping this takes a little mystery out of these boxes, okay? Now that we've got the circuitry down, just a basic understanding of what these circuits do, now we can understand what happens inside this little box. What happens inside this little box? All righty. Now on a zone valve control, it's the same thing, only different. It's a bunch of low voltage switches and a transformer in one box. All right, there's no excuse me, there's no line voltage on any of these on this particular box. In the newer, you'll see some line voltage outlets in the future, I believe. But in this one, everything's kind of low voltage. We have, I'm going to show you a couple things here. Again, isolated end switch. We have our zones, okay, our zone input, and then we have 4 terminals down here for our zone valves. All right, for 1 and 2 are always going to be power. All right, and then 3 and 4 are for the end switch. So say you're wiring this up to a zone sentry zone valve. Okay, 1 and 2, wires from 1 and 2 are going to go to the power terminal on the zone sentry, and then 3 and 4 are going to be wired into the end switch terminal on the zone sentry. So what happens when we get a call for heat? Call for heat, thermostat closes, okay, thermostat closes, that's the switch. The power supply's over here, okay, and the load is basically going to be the motor on that zone valve. So thermostat closes, the power supply delivers 24 volts to the motor on the zone valve. And that motor is going to open. When that motor opens, it's going to close the internal end switch. And now we've got a second circuit. We close the end switch. That end switch is connected to 3 and 4. All right. Several things will happen then, but primarily what's going to happen is we're going to close the isolated end switch here, which will cause, so that will cause something in the boiler room to fire. But we're also going to close this end switch over here, this pump end switch over here on the lower left. And when that closes, that is a dry contact. That pump end switch is a dry contact, a line voltage contact. You'll have to bring line voltage into it, but we can connect our system pump to that pump end switch if we choose to. All right, so end switch closes, okay, and that will cause 2 other switches to close, the isolated end switch and the pump end switch. All right, now this guy right here, the zone 4 pump end switch, you can see right there, it's a common, normally open, and normally closed. Common, normally open, normally closed. So right away we know that's a single pole, double throw switch. That's an either or switch. And it's connected to zone 4. Now zone 4, if you look over here, is the priority zone. So if we had domestic hot water priority and something on zone 4 called, that switch, which was in the normally closed position, will kind of go like this and go to the normally open position. All right, what was closed is now open, what was open is now closed. We can use that switch, and we're going to show you in 2 weeks, we can use that switch to run 2 separate circulators, one for the zoning and one for the indirect. We don't need any additional controls to use this with an indirect with 2 separate circulators. We'll use that zone 4 end switch to make that happen. In fact, you can actually use 3, you can use this to run 3 circulators depending upon your needs for a system. And it has a 5 amp max up to 1/6 horsepower. So it can run a pretty decent sized circulator. So that's something we'll dive into in the next session in a couple weeks. And here we show switches in series in a zone valve controller. It's kind of the same thing. So you've got the boiler high limit. Okay, there's a switch. Thermostat normally open. Your zone valve end switch is normally open because, again, it's not doing anything. The zone valve actually has to manually open or has to automatically open on a call for heat in order for that end switch to close. So again, you'll see a lot of switches in series. Very good. This was a quick one. I hope this was useful for you. It was only 38 minutes, but it was still pretty good. Any questions you folks have? Again, it may have been very basic for a lot of you, but it's all what we have found is we need to really need to set the table, so to speak, before we can jump in and actually have dinner. So anybody who had dinner at Thanksgiving, you know how you got to set the table first before you can dine. So we wanted to make sure everybody's kind of up to speed and we all have a same starting point. Can you explain the transformer smoke again? Well, it was kind of a joke. There's really no smoke in it. But if you overload the transformer, something inside fries, the smoke comes out, it doesn't work anymore. But it's not really smoke that makes that transformer transform line voltage into low voltage. It's just the coil. So I presume you knew that, Drew. But anyway, We are for the next two sessions. I just wanted to give you some basics on the next two sessions here. December 7th will be our commercial focus, and that will be on proper expansion tank sizing and selection. And Brett Zerba and Rich Medeiros will be running that program for you on December 7th. And then on the 14th, we will come back with our residential focus, the deep dive on the switching relays and the zone valve controllers. All right, and that'll be coming up on the 14th. So a lot of good questions here. Let's get to them. Is the line voltage delivered directly to the zone valve? Through the zone valve controller? No, it's low voltage, because we have line voltage and low voltage zone valves. When using the ZVC, it is a low voltage zone valve. It's a 24-volt zone valve. So no, there's no line voltage directly to the zone valve through our ZVC, Daniel. Let me know if that answers your question. Can you power a zone board from another zone board? Asked Kevin. We have EXP controls, zone valve controls, and circulator controls. EXP stands for expandable. They're expandable in terms of communication, but you do have to power them. You have to power them separately. All right, each needs to be powered individually. The communication is low voltage. The communication is simply 3 wires. You'll see a terminal on our expandable relays that says ABC, right? For the 3 wires, ABC. ABC to ABC on the next one, then you just daisy chain, then from the same set of terminals, ABC to ABC on the next one, and so on, however many you need. What that does is it basically means all of those relays don't have to talk to the boiler. Those relays will talk to the primary control. The primary control is connected to the boiler, and that's what tells the boiler to fire. So if, say you've got 4 controls, one zone on the 4th control calls for heat, all right? It just simply says, hey, there's a call for heat, click, 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 and then the main or the primary control that's connected to the boiler will tell the boiler to fire. So that's kind of how that all works. So all of them don't have to go back to the boiler. So, but each one does have to be powered individually. All right. Will the next webinar introduce power stealing components and/or resistors? Yes, Darren. We will get into power stealing thermostats and the resistors and what they do and when you might want to use them. That's the nest in a nutshell right there. And they'll tell you specifically what kind of a resistor to use on the thermostat terminals to help that work. So yeah, we will get into that in the next time. How does a dry contact work exactly? Well, think of a thermostat. If you were holding a thermostat in your hand, okay, there's no power coming from those 2 terminals, right? And the switch is open. That's a dry contact if you want to think about it, right? In terms of you have to bring power to it for that switch to be meaningful, right? Because if that switch were to close on its own, well, nothing's going to happen. You need power from another source to go through that switch to turn something on. The terminals on a pump relay, okay, when you connect the circulator to the terminals on a pump relay, there's power there. Okay, there's power at that switch, so you don't have to bring in external power. It's powered internally. All right, let me know if that makes sense to you. But that's kind of how that's how that one would work. So a dry contact, you have to manually bring power to it. A wet contact, I know a powered contact, a powered relay, like the circulator terminals on an SR. There's power there. You just connect your circulator to it, and then when the switch closes, you got power there. Okay. Zone valve motor uses 24 volts. Again, there are line voltage zone valves and low voltage zone valves. Residentially, we use low voltage 24 volt zone valves. So yes, whether it's the Takeo 571, that's a 24 volt zone valve, as is the Zone Sentry, etc. Okay. Isolated end switch. Basically, that's just it's a dry contact that it's when something else happens, then that thing closes. It's something internally to that relay causes it to close. So it's isolated. You can't put something, well, you could, I suppose, but you can't put something in there to make it close. Now you can't actually. What makes it isolated is that the only thing that can make that switch close is something internal to the control. In this case, let's say in the case of a zone valve controller, a ZVC control, the only thing that can close that isolated end switch is the end switch on the zone valve closing. That contact closes a circuit that will allow that isolated end switch to close, and then something downstream, the boiler control, which has a power supply and a load, all right, then that switch, that isolated end switch, is for that boiler control to do what it has to do. So the only things that can make that isolated end switch close is something internal to the zone valve control or the pump relay. Let me know, Kevin, if that makes some sense to you. Good, some good questions here, folks. Good questions. All right. Keep them coming. Keep them coming, because we have plenty of time. I'll stay on as long as you folks have questions, and I'll answer them to the best of my ability. I know I'm not Dave, but hey. Anyway. What is a great example of an isolated end switch? Best one I can give you is the XX terminals, Daniel, on a relay, on a zone valve control, all right, or an SR panel. Those are the best examples I can give you an isolated relay, because that's what an isolated end switch is. All right, so if you just let's look at the XX terminals on a zone valve control or an SR panel, that's the best example there is, because that thing won't close unless something in the panel says close. You know, something has to happen to make it close, and it's isolated. It's just a dry set of contacts, and you need something downstream in another control, again, like the boiler control, to make the magic happen. Very good. I hope that answers your question, Daniel. Let me know. What's the difference between using zone valves and actuators and the effects it could have on the internal transformer? Zone valves and actuators. Darren, are you talking about zone valves or the little manifold actuators for a radiant manifold? Is that what you're asking? I want to make sure. Yes. Okay, great. No difference, really. It's just a math question, right? It's what's the power consumption of the zone valves you're using versus the power consumption of the actuators that you're using, and they're going to be fairly similar. You know, whether they're motorized or heat motor type actuators, they all have an amp draw or a VA rating. All right, you just got to say, what do I got for a VA rating here? Does that match the transformer I'm using? For example, the Zone Sentry zone valve, okay, is 1.44 VA. 1.44 VA. It's the lowest power draw zone valve on the market today. All right, lowest power draw on the of any zone valve on the market today, and you can put up to 12 of them, okay, on a 40 VA transformer. If you're to do the math, that's okay. That works. Yeah, 12 at 1.44. Yeah, we're good. We put up to 12 of them on a 40 VA transformer. The 571 zone valve, 24 VA. Yeah, it's the highest zone. It's the highest power draw zone valve on the market today. We don't like to play in the middle. We'll give you the most power consumptive or the least power consumptive zone valve on the market today. Either one. So you can put 3 of those on a 40 VA transformer, even though the math doesn't work, right? The math says no. I can put 2 of those on a. Actually, I got probably 1 of those on a 40 VA transformer. You know, 40 VA, 24 VA. If I put 2 of those, that's 48 VA. That's going to let the smoke out. That's bad. Now you can actually put 3 because of some interesting stuff we did internally to the 571 zone valve. The amp draw that is not constant. It's intermittent. It's intermittent, meaning there's a little internal switch inside that will open and close as the piston that operates that zone valve kind of goes down, and it'll cause that internal normally closed switch to open, cutting the power draw from the zone valve or from the transformer. And then that thing will start to close a little bit, that switch makes again, and we push back down. It's a slight oscillation. It doesn't impact flow or anything like that, but it does interrupt the power draw. So when those things are when those things are open, their power draw is intermittent. And what we're doing is we're playing a shell game with the VA, which allows us to put 3 of those on 140 VA transformer. The worst thing that could happen in that instance is when all 3 of them come on at the same time, which would only happen on startup or when you're coming out of a power outage. Now, if anybody's put in a 571 zone valve and you've had say you get 3 of them on there and you're waiting for them to open them on system startup, you're waiting, baby, you're waiting. That's the impedance protection coming into play. The impedance protection cuts the wattage or cuts the voltage rather going to those zone valves. It has the net result of slowing the zone valve action down to the point where it can be painful waiting for those things to open. You're waiting, you're waiting, you're waiting, you're waiting, you're waiting. They finally do open, but that's only because all 3 are trying to open at the same time and we're protecting the impedance protection is protecting the transformer. That's the only time that'll happen. Otherwise, normal operation, they're opening, they're closing, and again, you're playing a little bit of a shell game. And you can run 3 comfortably on a 40 VA transformer. 4 is, no, don't do 4. 3 is good. 3 is good. All right, so Kevin says the system pump would be the load on the isolated end switch, right? Not necessarily. You could, but not necessarily. Typically, that isolated end switch, denoted by XX, goes to TT on the boiler, okay? Because that's an isolated low voltage end switch, and what that's designed to do, it said, hey, the relay's done everything it's got to do, okay? We've got the call for heat. We've told the zone valve to open, okay? The zone valve's now open. I've done everything I can do. The last thing is I close the end switch, and now we tell the boiler what to do. So what goes on the isolated end switch, the XX, that's going to go right to TT on the boiler, and then the boiler control is going to, you've got a power supply and a load there, another relay. So you get the power supply, which is another transformer in the boiler control, and a relay, which is in the boiler control. That relay is going to cause other switches to close, which will ultimately fire the boiler. And if you have tied the circulator if the circulator is still connected to the boiler, then that boiler control will fire the circulator. The pump end switch, the zone valve control has a pump end switch. Okay, that thing on the lower right-hand corner. Let me go back here and see if I can get the picture of it for you. Here we go. So up here, you'll see the isolated end switch, XX. That goes to TT on your boiler. That's pretty much the given. Just go right to TT on the boiler. Whoops, that's the wrong one here. Here we go. So again, isolated end switch, TT on the boiler. Down here, you have a pump end switch, which is a dry contact. There's no power there. You have to bring line voltage to one terminal of that dry contact. The other terminal goes to one of the leads on the circulator. The other lead of the circulator goes back to your L1, L2, to your line voltage, and it completes that circuit. Okay, so they're both dry contacts. The isolated end switch, again, it's low voltage. It's dedicated for the boiler. Line voltage can go down here. Okay, you can see it's a beefier terminal down below for that line voltage as well. And you can see the relay right there next to it. So I don't know if that helps answer your question. Okay, very good, very good. How many actuators can you put on a zone? Well, again, depends. On a radiant manifold, you know, that's kind of an interesting question. How many actuators can you put on a zone? I've always felt when I worked at Wurzbo, if you had more than like 4 or 5, say you had a 10 loop manifold, right? And you had these 4 loops on one zone, these 4 loops on another. Now it's more of a question of what makes more sense. Do I have a separate manifold with its own circulator or zone valve for each zone, or do I just put 10 actuators, 5 going to one zone, 5 going to the other? At that point, it's not so much how many actuators go in one zone, it's how many total actuators go in one transformer. All right, and that's going to that Chris or Jill's is going to have to do with what's the amp draw of the individual actuator on a radiant manifold. But again, typically you can get a bigger transformer if you need to. So I don't know if that answers your question or not, Jill, but it's a good question. Where would all three pumps be hooked up in zone 4? Okay, this is something, again, good question, Jason. We're going to get into detail on that in the excuse me, in our next session. But real quickly, let me give you this. All right. So let's say I'm bringing power to the pump end switch here. If I'm going to do 3 pumps, okay, I'm going to do another. Let's put a jumper here to the common. Okay. Bring the jumper there to the common. And let me make sure I get the. Okay, choose pen color. Let me go red, see if that helps. So here we go, right to there. Now I'm going to do a jumper to the common. Okay. Now I've got normally closed, right? So this switch right here is normally closed, right? So here, what I would do is if I had my system circulator, my heating system circulator for my heating zones, okay, I'd wire that like so, okay? And this is L1, this is L2. That's just your line voltage, okay? So think about this. Zones 1, 2, or 3 call for heat, right? Zones 1, 2, or 3 call for heat. Yeah, the isolated end switch closes, and that goes to TT on the boiler, okay? TT on the boiler, like so, and that'll fire up the boiler. When zones 1, 2, or 3 call, and the end switch here closes on the zone valve, then we close this switch here. So the pump end switch closes. So now my circuit's complete. I have switches in series, right? Both switches are complete. My system circulator turns on. Now, what goes to the normally open terminal? That's going to be my other circulator, okay, for DHW. And I'm going to connect back to L2. So this is my DHW circulator for my indirect, okay, not the recirc pump, but that's for the indirect, okay? And that's connected to zone 4. All right, I need to put a little jumper here as well to simulate an end switch because there's no zone valve connected there. When zone 4 calls and I'm in domestic hot water priority, okay, what's going to happen essentially is this. This normally open terminal will now close. Okay, the switch is literally going to go click like that. What was closed is now open. What was open is now closed. Now this circulator stops and then this circulator starts. All right. So I've done that either or thing, Now, if I wanted a third circulator, let's say I had a primary secondary on a cast iron boiler. Okay, a cast iron boiler. Now the piping arrangement, just think of a loop from the Gazzota hole on that boiler back to the Gazinda hole on the boiler. And then I have closely spaced T's elsewhere, right? I have closely spaced T's for my heating system. Now in this case, I'll have another primary circulator. So actually, I just have a second circulator connected here to that normally closed terminal. So when there is a call for heat, my heating system circulator will go on and my primary loop circulator will go on. And we have to imagine closely spaced T's here. And then when there's a call for domestic hot water, both of those circulators will shut off and my domestic circulator will come on. So there I can control 3 circulators with 1 control. Again, it's kind of without a boiler schematic, I want to make sure that it's hard to envision that, but again, we're going to see that in 2 weeks in great detail. All right. Very good, very good. Are there 2 boilers or can the same boiler heat the domestic and the hydronic heating? Yes, you can, sure. That's done all the time with a residential boiler. You just got 1 boiler, all right, and it's either making heat or it's making the domestic hot water, either or. And that's where that single pole double throw switch that's right down here comes into play. All right. Very good. Again, we just shut the circulators off for the heat and turn the circulator on for the domestic. So whatever the boiler was doing, it's not doing anymore. It's making everything for the domestic. How many circulators before we exceed the power ability of the box? Well, that is pretty straightforward. Let's see, erase all drawings. That's right here. It's just up to 1/6 horsepower, 5 amps max. So just check the amp draw on the circulator. And like the little double O's, they're tiny in terms of amp draw. 0.71, I think, or something like that. I have to look that one up, but the amp draw on those is very, very low. But it's 5 amp max. So it's basically the size of the circulator. And 5 amps, you're gonna pretty good size circulator there. Okay. Can I use one thermostat to control more than one zone of heating? One thermostat to control more than one zone. I'm struggling with the question there in terms of, then it wouldn't be more than one zone. It would still be one zone because one thermostat controls one zone, right? They could be piped up differently. You could have, you could link two zones together, yeah, but it would still be one zone, right? It'd still be one zone. Could you use a 3-zone pump controller in your scenario and send a signal from the ZVC to start the pumps? Yeah, I mean, sure. I think I know what you're saying is could you have the isolated end switch on a zone valve control feed the thermostat terminal on a multi-pump relay? Well, yeah, sure you can. Absolutely. Yeah, absolutely. And at that point, you'd have a circulator connected there, and you'd have to have a reason for doing it. But there's no reason that you couldn't. I mean, that isolated end switch does not have to go to TT on the boiler. It could go to, it's a dry conduct, just like a thermostat. You could put that as the input to a zone, an SR panel, a pump relay, and have it turn that pump on if you wanted to. Sure, you could do that. You could do that. Thermostats with 2 sensor ports. Thermostats with 2 sensor ports. You'll find thermostats that have the ability to take a floor sensor, often used in radiant heating. You could have a terminal for a floor sensor if you wanted to put that in there, and then that would be additional input. And at that point, you've got a thermostat that will have a sensor in the floor, but it's also an air sensor, an air temperature sensor. And that's done with radiant systems for safety. All right. Like say you want to maintain, typically they'll have a minimum and maximum floor temperature setting. All right. A minimum temperature, so we don't go below that, and a maximum, we don't go above that. Now think about that for a second. Let's say you got wood floors, all right, and you don't want to run into a situation where little Timmy looks at the thermostat and goes, ooh, buttons, and he turns the air temperature up to 95 degrees, all right? Well, okay, he sets the air temperature to 95 degrees. Bam, that thermostat goes in, kicks into action, everything's going because we got to satisfy that thermostat. Well, maybe we have nice oak floors or something like that, that we don't want the surface temperature to get above 80 degrees, all right? It's got nothing to do with water temperature, just the surface temperature of the floor. We don't want it to get above 80 degrees. Well, what that floor sensor is going to do, it's going to say, all right, they've set the max to 80 degrees. I don't care what the air temperature thing is saying. I'm going to say stop at 80 degrees. We don't satisfy the air temperature. That's not my problem, all right? So it's a safety for protecting floors from maybe getting overcooked by someone setting the air temperature up ridiculously high. And usually that's just done by mistake. It also features a low limit as well. And this is important in situations where maybe you have a radiantly heated great room that suffers from solar gain. You can't do anything about the sun. The sun is the sun, right? And it's going to heat up that room. But what happens often when we've got a room that's been heated by the sun all day, that solar gain, the radiant system hadn't called at all. That floor can go dead cold. Sun goes down, all of a sudden, I got a cold floor. It might take a while to get warm again to heat that room. What we do with the low limit is we said, okay, I don't care. Yeah, we're not calling for heat. I get that. But we don't want the floor to go below 70 degrees or whatever. So that when the sun goes down, we don't have that far to go to get back to comfort level. So we maintain a 70-degree floor surface temperature. Now, is the room going to be hot? Yeah, but you know what? The floor didn't make the room hot, the sun did. And there's nothing we can do about that. What we're doing is we're trying to minimize the catch-up time when the sun goes down. So that's where you'd see a floor sensor in a thermostat in a radiant system. It's a low limit, high limit. Now, some instances, a floor sensor might just maintain a specific floor temperature and we don't even have an air sensor in there, and that's fine too. That's done often in bathrooms or areas where the radiant is not the primary source of heat. It's just there to condition the floors and keep them nice and keep them not cold, basically. And then it's just forget the air temperature. We set the floor temperature at 72, 73 degrees, and that's that. And that can be done as well. Cool. Excellent questions, folks. Excellent questions. I'm very pleased. I'm very pleased. Okay, hoping this is helpful. Again, any more questions you have out there, type them on in. We've made it for our full hour. So, but again, I'll stay on as long as you want, as long as you have questions that I know the answer to. All right, I'll give you my best. All righty. And we had a big group today, over 100 people today. So thank you. I hope it was useful for you. Let me know. Type in a little, just a little, if you're still there, just type in a little. Was this useful? Was it what you wanted? And what are you looking for the next session? We've got a couple things here as well. That zone 4 pump end switch is going to be an integral part of the next session, so you really understand what that does and how it works. I think you're going to find that really kind of cool. You can do a lot of interesting stuff there. And again, if you can control up to 3 pumps if you want to without a zone pump control, just off a zone valve controller, it gives you a lot of flexibility. All right. And yeah, again, Ralph, we'll get into the zone controls in greater depth next time. But again, we wanted to get the table set before we bring out the turkey. And not to say Dave's a turkey, all right, because Dave's going to run the next one. He's not a turkey, but he's the main attraction for the next one. And we'll also talk about Nest and smart thermostats, okay? We're going to definitely talk about those and what they do, and basically primarily not on the operation of them because that's Nest's business, but how they interface into what we offer. We'll get that done for you as well on the next one. Very good, very good, Jerry. Thank you. That's very kind of you to say. Appreciate that, Jerry. Yeah, Vincent, you're right. It's basic, very basic. We wanted to get again setting the table for the next one. Excellent. Yeah, the electrical side of hydronics, yeah, Darren, you're right. It is, again, like I said, I didn't really I understood that relays made, connected the thermostat to the circulator and the boiler, and it made everything happen. But I never really got into the depths of it until I actually had to teach it. All right, because it was always that magic box on the wall that made everything work. And hey, it's a box, right? How it does it isn't my problem until you need to know. So it's important. The date for part 2 is going to be December 14th, Tuesday, December 14th. You can go to the TACO website and sign up for that right now if you want to. Yeah, just go to the training tab, look for TACO Tuesday, and then sign up for TACO Tuesday on the 14th. Ralph says it's not just smoke, but rather magic smoke. I don't know if it's truly magic smoke. It's special smoke. It's factory smoke. Okay, you can't make your own smoke and put it in there and bring a dead transformer back to life. It's a special blend of factory smoke, right? A combination of Kentucky bluegrass and, well, never mind. We don't need to go into that, but you understand. Here's a side question. How is TACO managing with supply chain issues? The very best we can. And it's a daily thing. I'll tell you what, I'll just tell you what the deal is there, Darren. It's a day-to-day thing. One day they're telling us where we're going to be 6 months out on something, and the next day we'll get a message that says, oh, we got them. Yeah, we're sending them. Okay, great. It's a constant management situation where we've got a team of people that are working every day to make sure that we can keep up as best we can. There's some things that are going to be a little late. That's just the way it is. But we're doing everything we can to make sure we give you the stuff that you need. So could it be better? Yeah. But you know what? From what I'm hearing out there, our situation could be a lot worse than it is. And we're very thankful for that we have great relationships with our vendors, and we have some really talented, hardworking people making sure we keep the pipeline full for you. So that's the best answer I can give you right now. Tomorrow may be different. You never know, but I don't think it will. We've got good people doing good work to make sure we stay as, are we in the ideal position? No, nobody is. But I like our position right now compared to the rest of the industry, if that helps you at all. Very good. Very good. All right. Excellent, folks. Hey, thank you so much for being with us. I do appreciate the gift of your time today. It was a pleasure to spend this Tuesday with you. And looking forward to 2 weeks from now. So we will see you again in 2 weeks on December 14th for a deep dive into these little control boxes. And look forward to seeing everybody there. And hope you all had a great Thanksgiving and are getting ready now for the Christmas season or the holiday season. They're already playing holiday music on the radio. Actually, they were playing holiday music on the radio right after Halloween. I don't know if any of you heard that, but they were playing holiday music on the radio 24/7 after Halloween, which really freaked me out. I said, that's a little too early for me. But anyway, have a great couple of weeks. We will see you December 14th, and take care, everybody. Enjoy. Thanks for being with us.
Good afternoon, everyone. Welcome to Taco Tuesday. It is December 7th, and it's the 80th anniversary of Pearl Harbor. Not that I was around, but maybe, well, anyways, quite an event. I had the opportunity to tour that museum out there or place in Pearl Harbor, and but put it on your bucket list if you ever get a chance. It's quite the place. Anyways, Brett Zerba, applications engineer with Taco. Most of you, I've been looking at the names that are popping up here. I have been through some of these before, if not, hopefully all of them, but I kind of doubt it. Hopefully anyways, thank you for attending. We really do appreciate it. I will be moderating today's event, today's webinar. Rich Medeiros will be the main presenter. So I will be monitoring questions and bringing them up with Rich as we go towards the end. Pertinent questions when they come up, I might answer some directly to you. So if you do type in a question, I may send you the answer privately. So please, watch for that. So if a couple of you can raise your hand so we know that you are seeing us and hearing us, because Rich and I, we always have issues. Oh boy, good. Thank you. There's Ada and others are putting their hands up. So good, Art. Thank you, Art. So good. That's a good sign. You never know with technology, especially for Rich and I. I don't know. We seem to have more hiccups than most. Hi, Craig. Thank you. Again, today's presentation's on expansion tanks. It's one of those subjects that pieces of equipment that sometimes gets forgotten, but it's very, very important. And Rich is going to get into that. Very, very important in systems for different reasons, for a couple of different reasons. And Rich will cover that for us. So there are no handouts today, but 24 hours after today's presentation, look for your email and you should get a copy of the recording. It is being recorded, as well as a PDH certificate if you can need it, or if you need it for yourself, or if you want to frame it and put it, on your office wall with the 30 other ones that you have from Taco. As you know, Taco is a privately held company, third generation. Johnny White Jr. is currently the owner. We are headquarters in Cranston, Rhode Island, but we're a worldwide company. We have places in Switzerland. We have places in Canada. We have places in Italy and other places. Vietnam, we have a foundry in Vietnam that does stainless steel work for us. So we are worldwide. People think of us sometimes as the little guys, but we're a lot bigger than people think, But remember this, we are the green pump guys, So anyways, I think I've done enough of my introduction here. And please type in the questions as we go. Rich is as knowledgeable as anybody on this subject and any HVAC hydronic subject. I guess that's about it. Rich, take it away, my friend.
Well, thanks, Brett, for that great introduction. I'm actually doing a quick test here to make sure that my pen is working properly and that it's going out to the outside world. So hopefully,
looks just like me.
Does it look like somebody you know?
Yeah, I'm looking in a mirror.
Oh, good. All right. Well, we know that works. So, quick intro regarding myself for those that haven't met me. My name is Rich Medeiros. I'm one of the senior systems engineers here at Taco. I am a PE registered in several states, and I've been with the company. Well, I actually passed my 9th year anniversary, Brett, a couple of weeks ago.
Awesome.
Yeah, in November. So that's kind of exciting.
Seems like only yesterday, my friend, that you and I were working on the IDC. Not that everyone knows that. Anyways.
So that's kind of cool. and I've been in the industry for several years. So we're going to talk about expansion tanks this afternoon. And I have a very quick agenda here. Why do we need expansion tanks? It's one of the primary questions that come up. Types of expansion tanks, Boyle's law, touch base on that, which is the fundamental theory behind expansion tanks, expansion tank sizing, and then we'll make a quick selection. And what does the location of the expansion tank, how does that influence the expansion tank? And as Brett mentioned a moment ago, we do encourage you to ask questions during the presentation. You can type them in. Brett will ask me to pause periodically, and we'll do our best to answer the questions. And if we have some time left over at the end, we'll certainly answer some last-minute questions. So, Brett, any questions out there?
No, nothing
No.
yet, my friend.
Nothing. Okay. So here we have a very, very simple diagram for a hot water heating system. And as I have the title up on the top there, it says, why do we need expansion tanks? Well, I'm going to state the obvious. When you take a fluid, like today we're just going to focus our attention on water. If you think about water in a closed loop, pressurized piping system, when you increase the temperature of that water, it will expand. And if the water has no place to expand to, then the first thing might happen, and hopefully it does if it was sized properly, is that the safety relief valve, which I'm pointing to right here on the top of the boiler, that will open up and relieve the pressure in the system. But if the safety relief does not open and the water expands and it has no place to go, then it will break something. And usually in my life, it always breaks something that's expensive. It never breaks something that's inexpensive in the system. It always breaks something expensive. So why do we need expansion tanks? Well, the main reason is to allow for a place for the fluid, in this case today, water, to expand as a function of the rise in temperature. Now, it turns out that the expansion tank is also responsible for a couple of other things. It is responsible in concert with the fill valve to maintain the minimum pressure in the system. And it's also responsible for maintaining the maximum pressure in the system. And the physical location of the expansion tank determines the point of no pressure change. So if I point to the connection here where the pipe is connected from the expansion tank, and here's our expansion tank in this little example here, to the distribution piping, if you'll notice it's connected to the suction side of the pump. And that connection point is called the point of no pressure change. So a properly designed system, this winds up being the secondary pump in the system. This one over here is known as the primary pump. Generally speaking, we put the expansion tank on the secondary side of the system, on the suction side of the secondary pump. And that maintains a constant pressure. Now, as long as let's assume for a moment that the water in this case has reached its maximum operating temperature at this point, which would be 180 degrees. And as long as that temperature remains constant, then the pressure on the suction side of the pump will also remain constant. And that's because of the functionality of the expansion tank. So to repeat, expansion tank does three major things. It determines it allows for the fluid to expand. It determines in concert with the fill valve what the minimum pressure in the system is going to be and what the maximum pressure is going to be. And then it also determines the point of no pressure change. So that's why we need expansion tanks. Okay. Any questions before I move on, Brett?
No, just a comment. I'm not sure. Hopefully everyone was aware of all of the things the expansion tanks do, or in the system. But that's a good time to re-emphasize that. That's for sure.
Yeah, it's worth stating the obvious. So it has a very, very important function. And someone reminded me of this. I think you and I talked about this. Someone reminded me of this a few weeks ago. One of the really cool things about an expansion tank is that it does not require any electronic chips. So we're not dependent on chip manufacturers to build our expansion tanks. So they're a very, very simple device. All right. So let's talk about the types of expansion tanks. I'm just going to list them here, but don't worry about the list. We're going to go look at some photographs in a moment so we can talk about the types. So the first type is called a plain steel tank. The second type is called a bladder style tank, and we have bladder style tanks in two categories, and most manufacturers do. The first category is called a full acceptance bladder style tank, and the second one is called a partial acceptance bladder style tank. And then the final tank is called a diaphragm style tank, and they only come in one configuration, and that's called partial acceptance. So let's take a look at some photographs and see what they're all up to. So here we have a plain steel tank, and as the name implies, it's just a steel container that has no bladder physically inside. You can almost think of it as a beer can lying on its side, although it will hold much more pressure than what a beer can will. It has a couple of connections on the left side over here, which typically would be connected to a sight glass. Kind of make this little imaginary sight glass over here, and the sight glass will give us the level of water in the glass, which is also the level of water inside this plain steel tank. So the water is at the bottom of the tank by W, and air is at the top of the tank over here. And plain steel tanks will be connected to the system ultimately. That pipe continues. And then on this side, it's usually connected to a special type of valve that allows the operator to bleed the water out of the tank and allow air to enter. So it's a dual function valve. It allows water out and air in. And most of the people will connect that to a hose bib, and it'll go into a floor drain inside a mechanical room. So we'll just kind of label that floor drain, FD for floor drain. So that's a plain steel tank. Now, plain steel tanks, by their very nature, excuse me 1 second. I'm losing my voice today, Brett.
Yeah.
Hold on. A plain steel tank. Let's see. We talked about the floor drain.
No
Well,
pressure,
whatever.
right?
Say, oh yes, the pressure, the minimum pressure is always atmospheric pressure. So because you're starting with atmospheric pressure, and when you fill the tank with water, the tank becomes fairly large. Usually in a plain steel tank as compared to a bladder style tank, the tank has to be somewhere between 2 and 3 times the size of a bladder style tank. We'll get into that in a minute. So any questions about the plain steel tank?
Yes, actually we have yes, we do. Would this be referred to as a compression tank like the old days?
Yes. Yeah, sometimes they're referred to as compression tanks. That's correct.
And this is a great question here. Well, this is in general to expansion tanks. Can the expansion tank be used as a on my home hot water line to increase the water pressure at the shower?
Well, the answer is yes and no. When you're talking about a residential system, generally the pressure that the residential system sees is a function of if you have say a town or city water supply, the pressure coming in from the city generally is regulated by a pressure regulator. And so the challenge comes in some, especially older cities that have older piping, they don't have that much pressure in the street. And so, and the expansion tank cannot add more pressure than what's available from the pressure regulating valve. So for example, if you needed roughly, let's say you had a 2-story residential building and you needed roughly 20 pounds of pressure for your system, if you only had 15 pounds available from the town pressure system, there's nothing you can do other than add a booster pump somewhere in the system. But if you have enough pressure from your municipal system, then you can set your system accordingly with your pressure regulating valve. So again, let's say you had 50 pounds from the street and your water system in your home only required, say, 30 or 40 pounds, two-story building, that's probably pretty common, to operate the plumbing fixtures properly, and then you'd have a pressure regulating valve, usually for your hot water heating system. So hopefully that answered that question.
Yep. And then I'm not sure if it's in all codes, but wouldn't you recommend that this type of product, any of the expansion tanks, be ASME rated?
Yes, we are TACO is a ASME, American Society of Mechanical Engineers certified manufacturing facility. So we do not manufacture any pressure vessels that are not ASME certified. So yes, we would definitely recommend ASME certified pressure vessels.
And then can you just scoot back to your drawing? We do have a question about, not your drawing, but your little design there kind of came up just as you were moving along.
Oh, okay. Hold on one second. Let
Yeah.
me go back there. Okay. We're talking about the little
Yeah,
diagram, this thing?
Yes. So what is when you look at the expansion tank, from the top of the expansion tank to the piping, there's a 0. What is that line in reference to?
Yeah, so that is the connection between the expansion tank and the main suction side of the pump, the piping. And the software that we're using is called the HSS software. I think that's what we call it, right?
Yep. Yep.
And the software puts in 0 inches, so by default. And so you would actually need to select the proper size connection between your expansion tank and your piping system. And I think the majority of our expansion tanks, don't they have like a 1.5 or 2 inch connection on it, Brett?
Yeah, I'll look it up while you're yapping.
Yeah.
Yeah.
So that's I probably should have blanked that out, and so that's a good point. I think I'll do that next time. I should have
Yeah.
zipped it out here so that because it obviously can't be 0 inches. It has to be something,
Yeah.
but that's one of the default values that's in the software. So I'm glad somebody pointed that out.
And while you're talking about design, do we need a pressure relief valve in a complex system in order to prevent damage to expansion tank and the expansion piping loop? That's probably something you'll get into later, right?
Yeah, as it turns out, you do need to have safety relief valves, and they're required by code, and you have to locate them strategically in accordance with the state, what's called, yeah, national, state, and local codes.
Excellent.
Okay. Let's see what we can erase here. So we went through this plain steel tank, and the next one is called a bladder style tank. And the first one we're showing you here on this cutaway drawing on the right. This is a full acceptance, full acceptance. Well, what does that mean? If you'll notice the green, we have the cutaway version, we have the green steel tank, and then we have the rubber bladder. That's this black guy right here. And then this void space between the bladder and the steel container is where the air goes, and inside the bladder is where the water goes. And up here at the top, that's where the connection is made to the piping system. And I believe, well, Brett's going to look it up in a minute.
Yeah, the majority, as you stated, the majority of them, when I just went to our website, is 1.5 inch connection.
Yeah.
Some of the smaller ones are 1 inch, some of the bigger ones are 2 and/or 3. But yeah, so
yeah, the majority of them are 1.5 inch connections. And the reason we call it full acceptance is, let's assume for a moment that the steel container in this case is 200 gallons. 200 gallons. I'm just going to put a G today for gallons. If the bladder can expand to the full volume of the steel container, which means it could also hold 200 gallons of water, then that means that it's full acceptance. Whenever the bladder capacity is equal to the steel container capacity, we call that a full acceptance tank. So I've made a little connection up here, 1.5 inch, that's for the piping system connection. Underneath this little collar right here is where the Schrader valve is, and that Schrader valve looks just like the Schrader valve that's on your car. The bottom of the Schrader valve, this one is actually a car tire Schrader valve picture. The bottom of the Schrader valve that we use actually is a threaded connection so that it bolts into the steel opening that's up here. So we have the outside steel container. We have the connection right here at the top where the pipe goes. We have the bladder that holds the water, and the space between the bladder and the steel container is where the air goes, and that's where you pre-charge the tank. We're going to get into that discussion in a moment. But you add air for the air side through the Schrader valve, which again is located in this little protective collar right here. Well, maybe this one up here is a little better. You can see it up here a little better. And so those are the major components of the bladder style full acceptance expansion tank. The next picture we're going to show you is for a partial acceptance tank. And the only major difference between this one and the previous tank is that the bladder can only hold a portion of the volume of the steel container. Again, here's the steel container that I'm pointing to. And let's assume that the steel container happens to be 200 gallons. The bladder, and I don't know what the exact capacity of the bladder might be, so the steel container might be 200 gallons. The bladder, for example, maybe is 50 gallons. I don't know until I look it up on one of our charts. But let's assume it's 50 gallons, and that's the maximum that bladder can accept. And because the acceptance volume is less than the steel container volume, 50 gallons, I'll put a little G over here, compared to the steel container of 200 gallons, that's where we get the name partial acceptance. And air, again, is here. I'll put a big letter A for the air. Inside the bladder is where the water goes, and then the air can be charged through the Schrader valve that's protected by this collar in the top. So the partial acceptance is very similar to the full acceptance, except that the bladder is physically smaller. All right. And then the last category is called a diaphragm style tank. And in this case, we don't actually have a bladder, or well, we don't have a balloon shaped bladder. We have more of a bowl shaped bladder, which we call a diaphragm. And in this case, oh, I should probably, let me go back and mention this. Let's go back here. In this partial acceptance and full acceptance, the bladder is serviceable, which means you can physically take it out and replace it with a new one. When it comes to a diaphragm style tank, the diaphragm, again, is this kind of bowl-shaped rubberized device. And that's called the diaphragm. It's connected to the inside, permanently connected to the inside of the steel container, and it cannot be serviced. So if the partial acceptance diaphragm style tank, if the bladder or the diaphragm should fail, then you have to replace the tank. You can't service it. You can't replace the diaphragm. So, and it's partial acceptance. It'll only hold a portion of the steel container, similar to the one I described a moment ago. If the steel container was 200 gallons and the diaphragm could only hold, again, this is the air side here. This is the water side down here. You could potentially rupture the diaphragm. So those are the major components of the diaphragm style partial acceptance tank. So before I go on to the next piece of the discussion, Brett, any questions?
Yep. You should be expecting this question. When should a partial acceptance be used in lieu of a full acceptance?
Well, I recommend
That's the $64,000 question, right?
Yeah, I recommend the full acceptance bladder style tanks for all applications. However, we're in a competitive market, and the reason we offer the partial acceptance tanks is because they're less expensive. And in a competitive environment, sometimes people want to be more competitive, and so we provide the same product that our competition provides. And the least expensive is the diaphragm style, which cannot be serviced, and that one is disposable at the end of its life. So we recommend the full acceptance, but we certainly understand that if money is an issue, someone may decide to put in a lesser expensive tank. They all do exactly the same job, by the way. If they're properly sized and installed properly, and we're going to get into that in a minute, they work fine. You run the risk in a partial acceptance of either destroying the diaphragm or destroying the bladder if you should try to put more fluid in there than what the design is capable of handling. Hopefully that helps answer that question.
Yeah, well, we got some great questions today. It's very interactive here. How do you know when an expansion tank bladder fails? Another $64,000 question.
Well, yeah. So why do bladders fail? Well, the majority of reasons for the bladder failure is that usually in a full acceptance, the amount of bladders that fail is very, very small. So let's go to a partial acceptance. If for some reason, let's assume that the Schrader valve we talked about a moment ago, Schrader valve is located up here. If someone should take the stem out of the Schrader valve and allow the air to escape, then if the system is pressurized, for example, let's just pick a number, say it's pressurized to 50 pounds, that 50 pounds of pressure will be opposed by 0 pounds of gauge pressure. It's basically atmospheric pressure. And so there's nothing to restrict the expansion of the bladder. So it could expand beyond its design capacity. Let's assume it had 50 gallons and the steel container is 200 gallons. If someone should take the Schrader valve stem out and allow the air to escape, then the bladder would eventually rupture if it fills up. And if it does rupture, this whole container inside here will fill up with water. And let's assume that the Schrader valve, someone did not remove the stem, but they inadvertently allowed the air to escape. Maybe they thought they were supposed to have 0 pounds of gauge pressure. And if they allowed the air to escape, then the bladder would rupture and the tank would fill up with water. And then if you depress the Schrader valve, water would come out. And that's how you know that the bladder has failed. Cool, huh? Excellent.
And I think I'm going to add, someone's asking about what happens when you put it on the discharge of the pump instead of on a closed loop system. But I think we should cover that when you get to the sizing. What do you think?
Yeah, let's, if we have, let's hold that question off to the side, Brett, and if don't answer it during the presentation, we'll answer it at the end. Okay, so let's touch base on Boyle's Law. Boyle's Law was published by Robert Boyle back in 1662. And here's a trivia question for you guys that are out there in the audience. What year did the Pilgrims sail in the Mayflower from England to what ultimately wound up being Massachusetts? Does anybody know what year they did that? While you're thinking about that, I'm just basically going to talk a little bit about Boyle's Law. States that the pressure of an ideal gas is indirectly proportional to its volume at constant temperature, and this famous equation is what Boyle came up with. And he said, in a closed container, the pressure and volume of an ideal gas at one point in the container is equal to the pressure and volume at another point. In other words, the pressure times the volume is a constant. And the pressure is always measured in pounds per square inch absolute. So I'm actually going to go to my whiteboard here.
1620 or 1492. Those are our statements.
Well, I'm going to give you a hint. It's definitely not 1492. 1492 is when Columbus, that's the date that was assigned to Columbus when he ran into one of the islands in the Caribbean. But yes, someone did come up with the correct answer. The Pilgrims came over here in 1620, which is only roughly 40 years, about 45 years, 46 years prior to Robert Boyle publishing his law. So that was about 360 years ago. Because last year we celebrated the 400th year anniversary of the Pilgrims landing in Plymouth. Since I happen to live in the next town away from Plymouth, it was a big deal. Okay, so let's look at a container for a moment. This is the before container. And so I'm just going to put in a B here for before, and then over here I'll put an A in for after. Well, maybe I should spell that out here, A-F-T-E-R. Now remember, we're talking about Boyle's law has to do with the ideal gas. So let's assume our container, check my spelling, Brett, because sometimes, as you know, I tend to screw up my spelling. Did I spell that correctly?
With the E, yes.
Yeah. So here we have a steel container that's 200 gallons. I'm going to put 200 gallons. And initially, this steel container is filled with air. So I'm going to put air in here, A-I-R. And let's assume that the pressure, if I had a pressure gauge, stick a pressure gauge over here. Let's say the pressure inside my steel container happened to be 50 pounds. 50. P-S-I-G.
Spelled that right. You
How's
are.
that? Pretty
Good
good.
spelling.
So it's a 200-gallon container, and it's 50 pounds of pressure. So what Boyle said was that if I take that same container and I compress the air, so now I'm going to take that same exact container, but the only difference is that I'm going to allow water to enter the bottom of the container. Let's say I've got a pipe over here, and my water level increases over here. So I'm going to put a W for water down here and an A for air up here. All right. And let's assume that I let in 100 gallons of water. 100 gallons. The question is, can anybody tell me what the pressure of the air is over here?
What was that formula? Remember the formula.
So basically, what Boyle said was the pressure, let's do it inside the tank here. He said that the pressure times the volume over here is going to be equal to, and I'm only talking about the air now, the pressure P2 times the volume over here. And if you recall, we said that the pressure has to be measured in absolute pressure. So those two are equal to each other. So if we simply rewrite his equation, then we can solve his equation for P2.
We got a lot of hundreds popping up.
Well, in a moment, I'm going to show you that that's not correct. P2 is going to be equal to the initial pressure times the ratio of the air volumes. So the volume over here, what was the air volume over here? I think we said that was 200 gallons.
Yep.
And then if I allow water to enter, allow 100 gallons to, how much air am I going to have for V2? Well, it's going to be 100 gallons, right?
Yep.
But remember, we said that the pressure for Boyle's law has to be converted into absolute pressure. So someone had close to the right answer. So we first have to take 50 plus 14.7, assuming that we're at sea level for a moment, then that would be 64.7. That would be the absolute pressure, P1 absolute pressure. So P1 would be equal to 64.7 pounds per square inch absolute, PSIA. So that's the pressure that we would double up here in this equation. So 200 divided by 100 is 2. So 2 times 64.7. I've got my calculator out, Brett, so I don't mess this up. 64.7 times 2 is going to be 129. So P2 is going to be equal to P2 is going to be equal to 129.4 pounds per square inch absolute.
We had, someone said about 130 PSI.
PSIA. And then to get it back to gauge pressure, we simply subtract 14.7 minus 14.7. That comes out to 114.7. So the pressure over here is going to be 114.7. And it's important that you recognize that it's the absolute pressure, PSIG. PS, there's a PS. Wow. Squeeze that in there, IG. So any questions about Boyle's law?
Nope.
All right, now for a quick question to make sure everybody's on the same page. What if I had exactly the same case, only instead of starting with a 200-gallon tank, I started with a 400-gallon tank? Would the final pressure be greater or less? Anybody want to take a quick guess?
They're all afraid now.
They're all afraid, yep. So if I started with a 400-gallon container and I only allowed 100 gallons of water to enter, then the air would go from 400 gallons down to 300 gallons, and my ratio would be 4/3, which means it would be 1 1/3 times the pressure. So the pressure would be less. The larger the expansion tank for a fixed amount of expansion, the final pressure is less. So if you're trying to decide whether you want more or less pressure in the system for a given amount of expansion, if you make the larger the tank you make, the final pressure is lower. The smaller the expansion tank you make, the final pressure is larger. And that was basically what we wanted to tell people about. Okay. So now let's get into sizing. Any questions before I go into the sizing?
Nope.
So when we size an expansion tank, there are 6 things we need to know. We need to know what the minimum or fill pressure is. We need to know what the maximum pressure of the system is, the minimum temperature, maximum temperature, the fluid type, which is very important, and then the system volume. So how do we figure out each one of these? Well, let's figure out the first one on the list. That's the minimum or fill pressure. That probably takes the greatest amount of time to figure out. So let's look at a very simple example. We'll have given a 75-foot tall office building. Let's find the expansion tank size. So we want to know what the minimum pressure is. So here I have a 5-story office building that's 75 feet tall, and our mechanical room is at the lowest level. So we're going to assume that our expansion tank is in this part of the building. And we're going to kind of stretch our imagination and assume the piping goes from the floor of the mechanical room. We know in the real world it probably doesn't, all the way up to the roof of the building. And the height of that column of fluid turns out to be 75 feet. So if I fill this pipe with water, and let's assume that I turn the water down, the pipe rather down here, and I get my bucket from Home Depot. I like the Home Depot buckets this week. Got a little valve here.
Orange. They're orange.
Yeah, they're orange. And I just let a few drops of water come out of that. And now I know the pipe is filled, and then I'm going to shut off the fill valve down here. Can anybody tell me what the pressure is going to be at the top of this piping system? If I put a pressure gauge up here, what is that going to read in pounds per square inch gauge? I'm also going to ask you in a moment, what is the pressure going to read down here at the bottom of our column of water in pounds per square inch gauge? Did anybody type in the pressure at the top, Brett?
A lot of zeros.
That's correct. It would be 0 pounds per square inch, PSIG, at the top of this piping system. Does anybody can tell me what the pressure is at the bottom of the piping system? So it's 0 up here.
I see 32.4.
I'm going to round that off and say the pressure down here is 32.5. And in a moment, I'm going to tell you how I'm going to show you the calculation, but I'll tell you what it is. And that is simply the height of the column of fluid divided by 2.31, because the conversion is 2.31 feet per PSI, feet, per 1 psi. So I'll just put a 1 in there, psi. So all we have to do is divide the height of the building by 2.31 and we get the pressure at the bottom. Now, we do not want 0 pounds at the top of the building. We want something greater than that. And the reason we want a pressure greater than 0 pounds is for a couple of reasons. We want to make sure we have enough pressure to push any air out at the top of the piping system through the air vents. And we also want to make sure we have enough pressure so that the pump, if there is a pump at the top or a valve, that they don't cavitate. And so most engineers will pick a pressure at the top of the building of somewhere between 5 to 10 pounds. And for today's example, I'm going to use simple math. I'm going to pick a value halfway between those two and make it 7.5 pounds. So if I add enough pressure from my fill valve that's inside the mechanical room to get 7.5 pounds at the top of the building, what's the new pressure going to be at the bottom of the building? Well, it's 7.5 plus 32.5, so that pressure at the bottom of the building is going to be 40 pounds. Any questions about that, Brett?
Nope. Ed wrote 40.
Excellent. So now we're going to go back to our little diagram over here. Well, actually, we're going to skip. Say the minimum pressure is the height of the building converted into pounds per square inch gauge. And we get that by taking the height divided by 2.31, which is 32.5 pounds. We want to add somewhere between 5 to 10 pounds for pressure at the highest point. We're going to use 7.5 pounds. If we add that 7.5 to the 32.5, then the minimum pressure is going to be 40 pounds. So I'm going to pause here for a moment in case anybody wants to take a screenshot or a picture, because this is how you figure out what the minimum pressure needs to be at your expansion tank and at the fill valve. So while folks are doing that, I'm going to move on to the next piece of the puzzle. Okay, I want to assume everybody had enough time to take a picture or do a screenshot. So now we've figured out what the minimum pressure happens to be. And it turns out it's also known as the pre-charge pressure. So when we ship an expansion tank from the factory, that expansion tank on the air side of the expansion tank is pre-charged to 12 pounds. And then we ship it over the road and deliver it to the site. And assuming for a moment that the tank is at the same temperature in the mechanical room before it's installed into the piping system as it was when it left the factory, then that pressure should be the same, should be 12 pounds. But in our example, the air side of the system needs to be pre-charged to 40 pounds because that needs to be the minimum pressure. And we have to pre-charge the expansion tank before we connect it to the piping system. And the pre-charge pressure and the fill valve pressure is all the same. 40 pounds for the fill valve, 40 pounds for the pre-charge in the air side of the tank. Pre-charge the tank before you connect it to the system, because remember, when it comes from the factory, it only has 12 pounds of pressure. By the way, you should always check the pressure in the expansion tank before you install it into the system and before you pre-charge it to make sure there are no leaks, because if it leaves the factory at 12 pounds, it should arrive at its destination at 12 pounds, assuming the temperature is the same. If it's not, if it's dramatically less than 12 pounds, then you probably have a leak, and you should test the tank for leaks before you put it into the system. So any questions about the minimum pressure?
Nope.
Good. So what's the maximum pressure? That's the next thing we need to figure out. Well, this is one method that you can use. There are multiple methods. They all are based on the same fundamental philosophy. And that is to say that we have at the lowest part of the building, remember we said our mechanical room is the lowest part of the building. And we have down here at the same elevation as the expansion tank, we have some type of piece of equipment that has a maximum design pressure of 150 pounds per square inch gauge. If that's 150 pounds, we don't want the piping system that's delivering pressure to that device to ever get to 150. So we're going to size the relief valve, or rather set the relief valve, safety relief valve, at roughly 10% below that value. So that means we're going to set the relief valve at 135 pounds. Let's go back here. I'm going to set the relief valve 135 pounds. So that's going to be the pressure at the discharge side of the pump. Actually, it's going to be, we want the pressure at the discharge side of the pump to be a little bit less than the safety relief valve setting, because if you're close to the safety relief valve setting, that relief valve can leak or drip, becomes a nuisance. So we want the pressure on the discharge side of the pump never to get above 130 pounds, because if that's never above 130, then we're not going to get to 135, which protects the equipment. If the pump has a pressure differential across it of 20 pounds, then the maximum pressure we want on the suction side of the pump is 130 minus 20, or 110. So the maximum pressure that we want at the suction side of the pump, which also happens to be the maximum pressure we want at the expansion tank, is 110 pounds. So now we know what the maximum pressure is at an expansion tank and the minimum or fill pressure at the expansion tank. And those are the two most critical, well, all the values are critical, I shouldn't say that, but those are the two most complex values to obtain. Any question about that, Brett?
Nope.
Okay. So now we know what the minimum pressure is, we know what the maximum pressure is. The rest of the values are pretty straightforward. The minimum temperature, sometimes referred to as the fill temperature, depends on the water temperature that you have in your building. And to be conservative, if you happen to be in the Northeast, like in New England, we know that the groundwater temperature is about 50 degrees Fahrenheit. So that's about the lowest temperature that you would have for your fill temperature. In our case, our simple example, we said it was a hot water heating system, and the maximum temperature was set at 180 degrees. So now we know what the maximum temperature is. The fluid type we're saying is water in this case, and that the system volume, well, the system volume is a tedious calculation if you try to do it manually. It's the volume of the water for the entire system, which includes the volume of the water in the piping, the equipment, the valves, anything that has water in it. And if you're using the HSS software, if you put the pipe lengths in relatively accurately, it will calculate the system volume for you. So you either do it manually, which is very tedious, or you can use software, which is very simple and fast. So now we have the 6 major things that we need to size an expansion tank. So I'm going to go live to our website. A little luck here. I'm going to go to our website over here, and I'm at our home page, and I'm going to go to selection tools, click on that, and then on the left hand side it says expansion tanks, and I'm going to zoom in. Let's see if I can zoom in here, and I'm going to fill in the values for our this is our Taco's expansion tank app. So the units we're going to leave at US units. The fluid we said was water. I'm going to initially leave the pipe material at copper. The system volume, I believe we said, Brett, was 2,000 gallons. The minimum or initial fill or operating temperature was 50 degrees Fahrenheit. The maximum is 180. The fill pressure, which is the minimum pressure at the expansion tank, is 40 pounds. The maximum pressure we said was 110. And then we're going to use a standard selection here for now. I'm going to click on search. Before I look at the search results, I'm just going to scroll down here a little bit to point out that the software has calculated what actually the first thing it did, whoops, what happened to my pen? The first thing it did was looked up the specific volume of the fluid at the minimum temperature and the specific volume of the fluid at the maximum temperature. Those two values in concert with the total system volume allows us to calculate the expansion. In this case, it's roughly, I'm going to round this down in a moment, you'll see why. I'm just going to call it 53 gallons. That's the water that would expand as a function of temperature. In other words, all we have is 2,000 gallons, whether you have it in a piping system or if you have it in a 2,000 gallon bucket, and you heat that water up from 50 degrees Fahrenheit up to 180 degrees, it will expand an additional 53 gallons. Isn't that cool? We're going to ignore the plain steel tank one for a moment, and we're going to say a bladder style tank requires a steel container volume of 95.2 gallons as a minimum, and the acceptance volume needs to be at least 53 gallons. So we're going to go over here on the right. I'm going to look at those selection the computer has made. So we'll notice that the first one is called a CA450-125. The CA is the tank configuration model. The 450 is the size in liters. And if you do a conversion, you'll find that 450 liters is 119 gallons. This other value over here, 125, that's the pressure rating of this specific tank. You can get them in other pressure ratings. If you look on our installation instructions or submittal data sheet, I think it's on, it shows you the variety of different pressures that you can choose. But for today's example, we're going to leave it at 125 pounds. The tank steel container volume is 119. That's greater than what we had down here, which we said was 95. And the acceptance volume, that means that the amount of fluid that the bladder can hold happens to be equal to the tank volume. Whenever the acceptance volume is equal to the tank volume, then that's a full acceptance tank. So that first tank selection will do the job. Second one will also do the job. It has a minimum volume of 112 gallons for the steel container. We need at least 95 gallons. It has an acceptance volume of 61 gallons. And now, if you'll notice, the acceptance volume is less than the tank volume. So therefore, it's called a partial acceptance tank. But 61 gallons is greater than the 53 that we need. And so that would do the job. We can say, yes, that's obviously. Hopefully the software has not made a mistake. And then the last one I want to point out is this guy right here. The tank has a steel volume of 57 gallons. Well, we needed at least 95, so we're going to multiply that by 2. We're going to have 2 tanks. 2 times 57 is 114. So we meet the requirements of 95 gallons. And the acceptance volume is 27, and since that's less than the steel container, then we say it's a partial acceptance, but you multiply that by 2. 27 times 2 is 54. If you recall, we said we needed approximately 53 gallons worth of acceptance or expansion. So that's pretty much everything I wanted to show you initially. Any questions?
Yeah, let's go over a couple of the questions. So the last one you just circled, 2757. I guess it can be a general statement that if the acceptance volume on this chart is less than the tank volume, then that's a partial acceptance tank model, I guess.
Correct. That's absolutely correct.
Right. And then when you were doing your calculations, at one point, how did you decide the pump delta T? Pressure drop in the system? Jonathan's asking.
Well, in this particular example, I'm assuming, let me go back to that. Can I go back to that? Yes, I can. Let me go back here. Where are we here? I think this is it. Yep. Okay, so in this case, if you'll notice, I said the maximum pressure that this pump could produce is 20 PSI at shutoff head. So in other words, let's assume for a moment that someone screwed up and they put a isolation valve on the pipe over here and they close that valve. And then they put another isolation valve over here and they close that valve. That means that there's zero flow through the pump, and that's called a shutoff head. So that means the maximum pressure that this pump could possibly produce is at the shutoff head. And if that's the case, it just happens that I picked the pump that had a differential pressure at zero flow or at the shutoff head of 20 PSI. That's where I came up with that number. The actual pressure differential that the pump can produce at shutoff is the one that you should use in your calculation. Does that help answer that question, Brett?
Yep. That perfect. And then here's an interesting question. If the chillers are on the roof and the expansion tank and pumps are a level below, how does that affect maximum pressure?
Well, the calculation is still exactly the same. And you take the height of the column of fluid above the connection of the expansion tank. So in this case, let's assume that the chiller is in the penthouse and the pump is one level below. And let's just arbitrarily say that the floor-to-floor height happens to be 20 feet. So the piping height from the center line of the, at the expansion tank connection to the highest pipe in the system might be the floor-to-floor height, which is 20 feet plus whatever the height is of the equipment on the upper floor. Maybe that's 10 feet. So the height differential would be 30 feet. And you would want to make sure that you so you use the same formula, only this case it's only 30 feet. So you take 30 divided by 2.31, which is about 12.9, we'll call it 13 pounds, plus you add somewhere between 5 and 10. Let's say you added 10 pounds. That means the pressure at the expansion tank wants to be 23 pounds.
Just because it's a little lower.
Yep.
And someone's asking, and this gentleman's last name is Schrader, believe it or not.
Hey, maybe he's related to August
I
Schrader.
know, he might be able to buy us a drink.
Yeah, I know.
Can you bring up the minimum fill pressure slide again? Something else popped up on the screen when I took a screenshot. So,
yeah, let me see if I can go back there. Let me erase this for a moment. And we want to go back to where we said it would be. This slide here, the minimum fill pressure and the pre-charge, yes. What's the question?
Nope, he just wanted to take a picture of it. Something probably popped up on his computer.
Yes. So let me, maybe I didn't mention this, maybe I glossed over it too quickly, Brett, but when we ship the tank, we ship it from the factory pre-charged to 12 pounds on the air side. And it's important that you do the calculation to determine what the minimum or fill pressure should be. And now you should pre-charge the air side of the tank before you connect it to the system. In our example, to 40 pounds. You have to take compressed air from compressor, go over to the Schrader valve, just like you would fill up a car tire, and you would pump that pressure up to 40 pounds. Test it a couple of times, and now you can connect it to the system, and it'll reach equilibrium fairly quickly because the fill valve is trying to maintain 40 pounds. The tank has got 40 pounds, and so there's a match. Okay, next question.
Can you oversize an expansion tank? I'm sure undersizing is not good, but what about oversizing?
Well, if you remember the little diagram that we put together for Boyle's Law, we said that if you made the tank physically larger, then the maximum pressure winds up being less. So in our example, the maximum pressure at the expansion tank was 110 pounds, and that was based on a tank volume of roughly somewhere between 95 and 100 gallons. That's what the software said. Let's just go back to that to make sure we're talking apples and bananas. So we said that the steel container needed to be roughly 95 gallons and the expansion volume was 53. Now, if I arbitrarily made that tank, say 200 gallons, just arbitrarily make it 200 gallons, we said that the maximum pressure would be less. It would never reach 110 pounds if everything was sized properly. It would be less than 110 pounds. So there's no penalty to the system if you should oversize the expansion tank other than cost and real estate. But you can put as big an expansion tank as you want in that system, unless you had some reason for maintaining a higher maximum pressure.
Can you go back to your PowerPoint? I think Mr. Schrader wanted us to go back another slide.
Yes.
Let's see. He said there's a one calculating the minimum pressure. Can you go backwards?
Yeah, hold on 1 second.
Yeah. The bat phone's on.
Sorry about that interruption, Brett. All
It's
right.
okay.
They wanted to see another slide?
Yeah, go back. Maybe there's one that says you had a slide calculating the minimum pressure. Well,
yes.
I guess.
Let's see. I think it's over. Yeah,
Yeah,
here it
that
is.
one there. Bingo.
Yep.
And then while people are taking a picture looking at this, so let's try to cover that statement. And this is from one of our reps, so I really do think it's probably pertinent. Maybe what happens when you install the expansion tank on the discharge side of the pump? in a closed system.
Let's go back to our little system diagram that we started with way back in the beginning here. Okay.
Bingo, bango, bongo.
Okay, so the expansion tank, if it's connected to the suction side of the pump, it's going to maintain. So if, let's assume that you have not started the boiler, just simply filled the piping system with the fill temperature of 50 degrees Fahrenheit, and you've got the minimum fill valve at 40 pounds, you've got the expansion tank at 40 pounds, the suction pressure on the pump is now 40 pounds. So far, so good?
Yeah.
Okay. If it's a variable flow, which in this case it would be because we have two-way valves on the terminal devices, if it's variable flow, the suction pressure remains constant, but the discharge pressure goes up or down as a function of the speed of the pump and the position of the two-way valves. But the suction pressure remains constant. And in order to maintain the proper operation of the pump, especially as it pertains to net positive suction head, we want to maintain a constant minimum pressure at the suction side of the pump. If I put the expansion tank on the discharge side of the pump, guess what's going to happen? The discharge pressure is going to remain constant. Now the suction pressure is going to vary. If the suction pressure varies as a function of the speed of the pump, the faster the pump runs, the lower the suction pressure is going to be, and you run the risk of the pump cavitating because the suction pressure is too low relative to the temperature and the pressure of the system. Hopefully that helped answer
Yep.
that question.
Yep, you're all caught up.
Well, we're just about at our ending point, Brett. We're hitting
Yep.
1 p.m. Do we have a last question that we want to answer, or it's your call?
Nope, I think we're all set.
Well, in that case, I'm going to take this just one quick moment here to thank everyone for participating in today's TACO Tuesday. Hopefully you got something out of it. And in a second, I'm going to turn it over to Brett. Hopefully you folks will have a great holiday if we don't see you. Are we going to see folks again, Brett? Not for TACO Tuesday, right? Before
I
the
think we
holiday?
have one more.
Do we have one more?
Yeah, you know what? We have one of your favorites, manual pressure drop calculations in 2
Oh,
weeks.
I like that one. Yeah.
Yeah.
When is that scheduled for?
2 weeks from today,
2 weeks.
Christmas
Well,
Day.
If
Christmas
someone
Day.
decides they don't want to participate in the next presentation, have a happy holiday to everyone, and hopefully,
Kimberly,
folks.
thank you very much. She answered all the questions, and she did a great job. So, and she's saying this was really good. So I wanted to make sure I shouted out to her.
Oh, good.
And
All right. So at this point, Brett, I'm turning it over to you. You can sign off whenever you want.
thanks, Rich. Great job as usual. As I said at the beginning, and I think some of you are finding out the more and more you listen to him, he is very, very knowledgeable, and his mathematics, many of us have had math courses throughout our lives, if not all of us, and Rich presents it in ways where it's understandable even for old people like myself. So anyways, thank you for your time. Hopefully we'll see you in 2 weeks. And signing off. Look for the email tomorrow. The recording will be available. Take care, everybody. Bye.